Hello everyone and welcome to the last session of the day. First talk is Narayan. We're talking about de Sitter, extremal surfaces and time entanglement.
So it's a great pleasure to be here back at ICTS, and I'd like to thank the organizers for this beautiful workshop and inviting me to speak. So I'm going to talk about de Sitter space and extremal surfaces and the structures they lead, time entanglement, pseudoentropy, and so on. Okay. So this is based on these papers specifically, but also earlier work, in particular this one, which so this is based on these papers, but also this earlier body of work, in particular this one, which began this whole thing. And so I'll talk about de Sitter space to begin with, DSCFT, which is where this whole thing sort of broadly fits in as context, and the entropy. And then I'll talk about what you get if you analyze the Takayanagi story in this context, and how they lead to pseudoentropy. In particular, analytic continuations and a version of the Lekois-Maldacen argument. And then in the very end, I'll talk about just aspects of this stuff in just quantum mechanics, which are entanglement-like structures with time-like separations. Okay, so in the last many years, since ADS-CFT, we've seen at a very broad brush level these asymptotic structures. If we have negative lambda, we get ADS-like asymptotics over there. The dual is a unitary Lorentzian CFT, which includes time. For flat space, we get a null infinity-like structure with an S matrix and its symmetries. For positive lambda, the natural boundary seems to be at future or past time-like infinity over there. And the dual then is a hypothetical Euclidean CFT with bulk time being emergent. Okay. So it's to be noted that if you look at the gravity dual of an ordinary Euclidean CFT, you would expect Euclidean ADS. So whatever this dual is, if it exists, is some exotic thing. At least that's what this would suggest. One might more generally regard de Sitter as a toy model for cosmology more generally. And some of this stuff I think will play out in that context also, but I'm going to focus on just de Sitter here. An interesting pointed question is to ask if one can think of de Sitter entropy, which is the area of the cosmological horizon, as some sort of holographic entanglement. Okay, so what do I mean? I mean, so this is a picture of de Sitter space. It's a sphere that's crunching and growing with time. If you draw one of these lines, the upper half is a Poincare is a Poincare slice. The two patches here are described by the Poincare slicing. If you draw both of these, this is a static coordinate system, and so on. And then for observers in these left or right diamonds, these lines are like event horizons, and the area of, but they are cosmological, and so the area of these cosmological horizons is de Sitter entropy, okay, as formulated by Gibbons and Hawking long back. In the current context, I'm going to base everything on the future boundary. So it's natural to ask, in the context of holography, with this point of view, is this, can we think of de Sitter entropy as some sort of holographic entanglement? Okay. In that context, it would be natural to ask if there are generalizations of Takayanagi pertaining to the future boundary. Okay. So this is what is going to be the theme of the talk. The answers, as calculations, are lead to a collection of interesting factoids. If you ask for an overall interpretation and a physical meaning and so on, I think that's still very much evolving, and you'll see. But I'll tell you what happens. Before we go there, let me just tell you a little bit about what the broader context is. Although the details are not going to be so important for what's to follow, it's useful to keep this in mind. So DSCFT was formulated long back by Erdmenger and Witten, and really spearheaded by Erdmenger. The idea is that you take future time-like infinity as a natural de Sitter boundary, and this leads to a Euclidean non-unitary CFT dual with bulk time being emergent. This is expected to be some exotic object because the gravity dual of an ordinary Euclidean CFT is expected to be Euclidean ADS. Subsequently, Maldacen in his well-known paper on non-Gaussianities argued that the structure of inflationary perturbations can be organized and recast as an analytic continuation about ADS, and this leads to a precise DSCFT dictionary, which is that the wave function, the Hartle-Hawking wave function of the universe at late times, subject to certain regularity conditions, is equated with the partition function of this hypothetical dual CFT. Okay. Bulk expectation values are calculated by the usual quantum mechanical expression, which is this, where we take the wave function squared and calculate this object. So this suggests that the bulk dual in some ways involves two CFT copies, two copies of this, whereas it's only one copy that is equated with this dual partition function. But if you take this as a dictionary and you ask what the dual is like, the dual turns out to be a ghost-like CFT in real sense. For example, the dual energy momentum stress tensor two-point function leads to a negative or imaginary central charge. Okay. So this is just obtained by doing standard ADS CFT-like calculations in this context. And a version of this was exemplified by Ananias, Hartmann, and Strominger long back in the context of the higher spin DS4 theory, and they argue that it's dual to an SPN, ghost-like three-dimensional CFT, which is an analytical equation of the Klebanov-Polyakov ON theory. Okay. So the details of this are not going to be so important for what follows, but this is useful to keep in mind. So we go back to ask whether one can ask for de Sitter entropy as some sort of holographic entanglement in this context and potential Ru-Takayanagi generalizations based on the future boundary. So a natural generalization of Ru-Takayanagi to de Sitter might involve the bulk analog of setting up entanglement entropy in this dual Euclidean CFT. So to give this context, what do we do in ordinary quantum systems? We take a subregion, or we take a constant time slice, we take a subregion, and then we trace over the environment, and this leads to the entanglement entropy of the subregion with respect to the environment. In ADS, we do the same thing. In principle, we take a constant time slice, look at the bulk slice, take a subregion here, and this says that the Ru-Takayanagi surface goes like this. So it sort of begins here from one endpoint of the subregion, goes in, turns around, and comes back. Okay. So there's a deepest point up to which this surface sort of goes in. That's the turning point, and that turning point sort of scales like the size of the system. So to follow that logic, in this context, what we want to do from this point of view is to apply this operational logic to this case. So we look at this dual Euclidean CFT. It's a Euclidean CFT, so it's got no time in it per se, but we define some boundary Euclidean time slice as what we want to call the constant time slice. And then we define subregions there and anchor these surfaces there, and then these surfaces might go in. They dip into the holographic time direction. This is one analog of what you might think could be done in this context. So you might think you get a picture like this, if you get a picture like this, okay? So this, yeah.
Sorry to interrupt, in this context, especially since boundary theory is just Euclidean and you arbitrarily chose some direction to be time, it's just more sensible to also take surfaces anchored at different instances of your time, right? Because no, I was just saying, because the boundary theory is really Euclidean and you just sort of arbitrarily said, this is a codimension one slice on the boundary, which is equal time. I could have just taken even surfaces anchored at, that's about as natural.
You could have done more general things. I'm looking at the simplest possible thing in some ways, and that simplest possible thing sort of gives interesting answers, it turns out. Okay.
You're discussing about how to define the boundary term, right? The bulk thing is well defined. So the boundary term is not, it's not an entanglement entropy in the state.
It's not an entanglement entropy in the conventional sense, but you'll see what this gives operationally, and then we'll revisit this. So for now, I'm going to just focus on the operational story to see what you get, and then we'll see what happens.
So it's possible for 2 points on the past boundary and the future boundary to not be connected by a space like geodesics, So
you'll see examples of some of this in what follows, actually. So just hold on to that thought, yeah. So this is what we would like to ask. You can actually do this extremalization in great gory detail in many cases, and what this shows is this interesting fact that surfaces anchored at the future boundary do not go back. This does not happen. There's no real I plus to I plus turning point for Lorentzian de Sitter. So these surfaces that you anchor here do not go back. They simply keep marching on. So what you can do just geometrically is leads to these following structures. One, you can find future past surfaces which begin here. Since they don't go back, you could ask if they end here. So these surfaces start at I plus and end at I minus. They are entirely time-like, and their area has an overall minus I, therefore, relative to ADS space-like surfaces. The other thing you can do is to look for no boundary de Sitter. So chop de Sitter in the middle and attach a Euclidean hemisphere to the bottom half, and this then is a Lorentzian de Sitter which sort of evolves smoothly from no boundary boundary conditions all the way to the future. Okay. Then yes.
How do you distinguish between minus I and plus I as the area of the surface?
At this level, you can't really distinguish. The imaginary part has issues. In particular, for example, in some of what follows, some of this can also be obtained by analytic continuations, and then the analytic continuation keeps the real terms all fine, but the imaginary part can switch signs depending on which way you analytically continue. But once you fix that analytic continuation, then you can talk about how things are relative to each other and so on, and that turns out to already have interesting structures. So that's what. So for no boundary, for the no boundary case, there are no boundary de Sitter surfaces which sort of where the top time-like part is the same as these future past surfaces, which then go this way, and then they join smoothly with the real surface that goes around the bottom hemisphere and therefore turns around. Okay. In the ADS to global or static de Sitter analytic continuations, you can show that the analytic continuation amounts to a space-to-time rotation. So you sort of start with ADS stuff and you sort of rotate it by 90 degrees and you get the de Sitter stuff. Okay. And that structure ends up being quite important in. So what do these things mean?
This is Euclidean ADS to
huh?
Euclidean ADS to.
It is Euclidean to ADS, but everything I'm going to do is in terms of a constant time slice always. So it ends up being Euclidean. Although the analytic continuation itself you can think of in the in the full Lorentzian thing. So, but I think I will get to that eventually. So what do these things mean? Compared to relative to the ordinary Takayanagi story, there are time-like components in all of these things. So they really, I think, are best thought of as some sort of new object, some sort of time-like object or time entanglement, or a pseudo-entropy. And some of this I'll try to make a little more precise. These are really entanglement-like structures with time-like separations. Pseudo-entropy for future purposes is this object that was defined by these people, Nakata, Takayanagi, Taki, Tamoka, Wei, in 2020. And is this object, you consider two states and you do a partial trace. Think of this thing as the transition matrix, do a partial trace, get a reduced transition matrix, and the entropy of the reduced transition matrix is pseudo-entropy. And some of these things I think are best interpreted in that light. So we get complex objects and so on from these extremal surface points of view. In the dual, if we believe this fact that we have this ghost-like theory as the dual, perhaps this is not so surprising that you get complex valued objects and so on. It's not. I don't think it's easy to analyze the full ghost theory in detail. It's, I think, a fascinating thing. But in various toy models, one can actually do many things. And so long back, I tried to generalize the replica arguments to C equal to -2 ghost CFTs, and this was top-rated two-point function leads to the real part of the entanglement entropy being negative. But there are subtleties here. There are technical subtleties, but also overall subtleties and so on. But there are much cleaner, much simpler toy quantum mechanical models that you can construct, where you can ask these sorts of things, and you can actually do very explicit analysis. And so just to give you a flavor of this, if you look at an ordinary spin, we define an ordinary spin by up is 1 and down is 1, a two-state Hilbert space. A ghost spin I'm going to define as this two-state spin variable with an indefinite norm. So an up-down is 1 and down-up is 1. And these indefinite norms, these indefinite inner products lead to negative norm states, and they sort of model a ghost-like system. In some ways, I was abstracting away the B0, C0 subalgebra from the BC CFT, and that's how I got these structures. Now you can go to an explicit basis of positive and negative norm states and study many things. If you look at an infinite ghost spin chain with certain nearest neighbor interactions, you can show that that leads in the continuum limit to the BC ghost CFT family. Okay. For entanglement, one could start with states defined in this fashion with these elemental units, define the density matrix, do a partial trace, construct the reduced density matrix for the remaining ghost spins, and then calculate its one-Neumann entropy. And so this is, you can do this in general for any of these finite systems. And if you look at two ghost spins, you have to be careful in defining, since there are minus signs and so on, there's a non-trivial metric, you have to define the norms and everything else here carefully. So the norms, for example, you have to contract correctly with this ghost spin metric. And there are minus signs here, for example, as you can see. And the reduced density matrix is defined by this partial trace in this way, again contracted with this indefinite ghost spin metric. And the one-Neumann entropy then is this object. It's traced rho log rho, but defined correctly with the correct contractions. Okay. Yes. It's not an entropy in the conventional sense, if that's what you can. It's not satisfying the properties of. It's not going to satisfy all of those inequalities. So it's not an entropy in the conventional sense. It's at best a generalized entropy. If you don't like the word entropy, you're free to call it, a pseudo entropy if you like, or whatever. It's not an entropy in the conventional sense. It's not going to satisfy all these inequalities because it's got, it's a complex object and so on. I think that's just a fair thing. When I began this, I was, motivated by doing the mechanics of entanglement entropy, but it's not, I think, an entanglement entropy. I think that is just a fair statement. To be clear, even here, this object, the adjoint in these systems is a rather non-trivial thing to define because these indefinite norms means that there are extra ghost zero mode insertions that have been stuck in to make things non-zero. And so this object really is also in some ways a pseudo entropy as I was defining it, as I just stated in the previous page. So this is just quantum mechanics. This is just quantum mechanics. There are detailed things there which again are interesting to look. So let's just hold on to that. I think I will get to that, but let's just hold on to that. Yeah. So there are many new patterns here because of all of these things. The central takeaways are that the negative norm contributions means that there is an imaginary part to these entropies, so to speak, or pseudo entropies if you like. Positive norm, the plus sign here, does not still mean that you get positive objects because you could break up this thing in many different ways, and the reduced density matrix still then has negative signs, and so you still can get imaginary parts here. And so even though the overall state is positive norm, you might still get complex objects. Okay. This is for one copy of this ghost spin theory, so to speak. If you take two copies, one can entangle identical ghost spins from each copy, and this leads to positive structures, it turns out, in these class of things. In this particular context, for example, you can see if you focus on just this subsector here, and you rewrite this in this fashion, this looks like two copies of a single ghost spin, so to speak, but I'm correlating them in a particular way, and then it leads to an entirely positive structure. And this you can show it's also true for two copies of general ghost spin ensembles. Okay. Now, this structure is just something to keep in mind. It's not going to play out in detail in what follows, but it's trying to think along these lines for the SPN theory or something might be a fascinating thing to do. I don't think you understand that very well. Okay, so on to, yes.
For the SPN theory, which is dual to Vasiliev, you can define a similar notion of some kind of pseudo entropy, is it?
So for a while, I tried to, we got this continuum for the BC CFT. We tried to do the same sort of thing to construct a lattice model for which might be engineered along the lines of the SPN theory and so on. And we were just having technical difficulties, and at some point we just sort of, I think it's an interesting thing to ask. There are technical things that go in here. For example, there's a version of the Jordan-Wigner transformation that we invented to make this work in some ways and so on. And I think there were things there which they're just technical things which we couldn't see getting across. But I think the elements are here. So I think there's something to be, I think there's something here which we really should sort of look at more carefully. Yeah. This is just ordinary quantum mechanics. Yeah. So so I think there's more that has to be done to really make contact with the de Sitter side. But I think the elements probably are here is all I'm saying. I don't think it's, I think there's more. Yeah. There's a way you can define, you can map this, you can take these structures and go to the PT symmetric norm, but this stuff, I want to make the negative norm states, the negative norm contributions on explicit, and so I want to keep this as it is. In the PT symmetric story, I think the point is to sort of map it to a completely positive, completely positive object, and that is a map, but here I want to just, I want to take this minus sign seriously. Wow, all right. Okay, so de Sitter. I probably will have to be a little quick, but so in the simplest things one can do is look at the Poincare story, and if you analyze this in the Poincare slicing, these are all these spatial directions. I pick one of them as boundary Euclidean time. Any of them could work. Set up the extremization equations, set up a subregion here, and so on. If you do the extremization, you find that there's a plus sign here which correlates with this minus sign, and this sign difference from ADS, this would have been a minus sign in ADS. And this sign difference from ADS is what leads to the fact that there's no real I plus turning point. If this object starts like that, this minus sign would have made it go this way. That doesn't happen. It sort of keeps going this way. Okay. If this parameter, this conserved quantity b squared is negative, then you can show that there are analytic continuations which essentially which from the ADS RT story. In the static case, I'm writing it in this way to illustrate that for r greater than L, this is the time direction, and that's the future inverse, and so on. Since these things don't go back, you could ask if they start here and end here at I plus and I minus, and these can be shown to exist. I know there's some story here, which I won't get to the details of, but these are basically future past entirely time-like surfaces that connect I plus to I minus. And these are essentially rotated versions of the Hartmann-Maldacena surfaces in the ADS black hole, which is what I was sort of motivated by in some ways. The area is pure imaginary here. This pertains specifically to to an equatorial plane as the boundary Euclidean time slice. You see the boundary here is a cylinder. So I could have also chosen this as this t direction as the Euclidean time slice, the boundary Euclidean time slice. If you do that, that is the same as any equatorial plane slice in the global system. You can just see that that is true. But in this case, also you can show that there are future past surfaces that connect these theta caps. So you take a boundary Euclidean time slice, define a cap here, a cap there, and there's the extremal surface that stretch from this cap to that cap over here. These are all entirely pure imaginary. And so they're entirely time-like, and so their area is pure imaginary. The other thing one can do is to ask for Hartle-Hawking type analysis, where the Hartle-Hawking no-boundary proposal says that Lorentzian de Sitter evolves in time from a no-boundary Euclidean initial configuration. So we cut global de Sitter in the middle, and at this mid-slice, we attach a Euclidean hemisphere, and the top half then joins smoothly with this hemisphere in the bottom half. So for what follows, this is the specific Euclidean continuation I will take. And now to play this game of extremal surfaces, I choose any of these equatorial planes at SD at the sphere at the future boundary. So that gives an SD minus 1. Now I define a subregion there, and I anchor surfaces there and see what happens. We've already seen that there are time-like future past surfaces that go from here to there in the entirely Lorentzian object. The top time-like part of that joins goes and hits this star equal to 0 mid-plane, mid-slice vertically for the IR region. And this then we join smoothly with a surface that goes around this bottom hemisphere. Okay? And the smooth joining is the consistency of this future past surface with Hartle-Hawking. Okay? So these then now do turn around, but they turn around to the hemisphere, not in the Lorentzian region. The Lorentzian region continues to have nothing, no turning point. There's nothing that can go back there. So this thing goes to the hemisphere, then turns around the hemisphere. If you do this, the bottom hemisphere is a Euclidean object. Its area can be calculated explicitly, and you can see that what you get is half de Sitter entropy. Okay, this is precisely half de Sitter entropy, and this is a straightforward calculation. And then there's a top time-like part. Okay, now, although Just to make sure,
it's half the de Sitter entropy regardless of the size of the interval you start with.
Yes. But there's nice things that happen for the IR surface, but for finite subregions, there are tricky things that go on, it turns out. I probably won't get to that, but we can talk separately about that. This is the IR region, so the maximal subregion at the.
This is not for some region on top.
This is specifically for this. I mean, what I'm drawing here is the, if you look carefully, there's actually a blue line sort of going along this. So that's actually the IR region. But the hemisphere contribution turns out to be the same for any finite subregion. For any finite subregion, yes.
But it's not just cutting the sphere into half.
It's not just cutting the sphere into half. But this one, but I'm going to focus mostly on that case where I'm looking at the maximal subregions. There are many things that have to be looked at very carefully for the finite subregions case, and I may get to some issues with that later, or we can talk.
But you're saying that the answer here is independent of that.
Yes.
Sounds so strange, right?
It's strange. It's strange, and it also, roughly speaking, what happens is the following. So if you want an intuitive answer for why that answer is the same, you look at a vertical. So if the IR region is a vertical plane, and this thing is this geodesic that goes like this for the DS3 case, for example. But if you look at a small perturbation there, this thing sort of tilts, and this thing tilts like that, and this thing sort of, the hemisphere part sort of tilts like that, and that still is part of a great circle in the hemisphere. Therefore, it ends up being this way. But there are details there which actually turn out to be non-trivial. But let's not go into that now. So this is precisely half-distributed entropy, but it emerges very differently from the area of the cosmological horizon for static patch observers that we're all familiar with. In particular, one of the hemisphere directions here is the Euclidean continuation of what was time in the future universe.
Sorry.
Yes.
So here, how is this last fact you said that it's independent of the size of the interval? It's not. How is it consistent with the fact that you can calculate entropy with conformal anomaly, where you would get the usual log sinh L sort of.
I think I will get to that at some point. So just hold the thought here. So for DS4, the total area of this no boundary surface is this thing. This part comes from the top time-like regions, and this part is the real thing that comes from the hemisphere. Okay. There are similarities with the wave function, the semi-classical wave function, or maybe more precisely the log of the wave function. So this thing is global de Sitter, but as we saw, the t-equal to constant slice in the static patch, in the static coordinate description, is the same as the global slice in any equatorial plane. So this half-distributed entropy also emerges for no boundary de Sitter static t-equal to constant surfaces. Okay. So this is the general thing. This is for DS4. We've seen future past and no boundary surfaces, and the relation between them is like this for these IR surfaces. The future past ones are entirely time-like, and you can see that they are twice the imaginary part of the no boundary ones, and the real part of the no boundary ones are half-distributed entropy. So in some ways, the no boundary ones are like one copy of the wave function that you might get, and the future past ones involve two copies in some sense. Okay. Now all of these surfaces, because there's no I plus to I plus returns, they necessarily have time-like components. And so when we talk about space and time intervals, we think of a time-like geodesic length as having an overall minus I relative to a space-like geodesic length. So we call this time length as time rather than minus I times space. It's a new thing. And so from that analogy, you might think that these things should really be thought of. These extremal surface areas with time-like components should really be thought of as some new object, a time entanglement or a pseudo entropy. Okay. It's useful to look at. It's instructive to look at DS3 to ask what this becomes. These expressions, they were not here on this page, but okay, but they're here. So for DS3, the future past surfaces pertain to the entirely global, the entirely Lorentzian global DS3, where I take some S2 equatorial plane, and then I calculate these extremal surface areas. And the area then is pure imaginary, and it looks like this. And you can see that this thing is twice the standard Calabrese-Riccardi answer with this imaginary central charge that's known for DS3. For the no boundary ones, the area is this object. So it's got this imaginary part and this real part, and this real part is half de Sitter entropy in this case, it turns out. You can write this as this combination where the C is this central charge. Okay? And now you can see that this imaginary part is basically what maps to C over 3 log L over epsilon, and this is for a half-size interval in a Euclidean CFT on a circle. And the real part then is something new. It seems to arise from some deep interior Euclideanization, some sort of something that encodes interior regularity in the Euclidean CFT dual. Okay, but this is not something that I understand in a real way. This is just what seems to be the case. Okay. Yes, because the imagery part contains. I can only think of them as in terms of 2 copies of some appropriate time contour and so on. So if you think of the time contour as going pure imaginary and then real, then this thing, the future past ones is this way, then this way. That's for the future past ones. I'm not quite sure. For the future past ones, I'm not quite sure. For the no boundary ones, I think I'll get to. Now, as an aside.
Also, this non-boundary calculation is different from the time-like entanglement entropy calculation by the Tadashi. And
good question. So this expression, as an aside, is something that I also noticed that we noticed this in the context of quantum extremal surfaces before. And this object is in fact the entropy for an entirely time-like entropy in quotes for an entirely time-like interval with T. So just to remind you, if you look at ordinary unitary 2-dimensional CFTs, the entanglement entropy is this object, where this is a space-time interval. For ordinary space-like intervals, entirely space-like intervals, delta T is 0. This thing is just this. This is the usual Calabrese-Riccardi answer, which is here. But for an entirely time-like interval, there's a minus sign here, and that then picks up a log of minus I, and modulo issues with the branch of the logarithm and so on. You get this expression, and this is basically that. Okay.
That, in a sense, explains why, regardless of the interval, if you are willing to consider.
Yes, exactly. So in this context, that explains if you like. But we got this, but then I really wanted to see if geometrically you can actually construct this, and that also actually goes through. But that's sort of what, from the point of the analytic continuation, that explains it in this context. But yeah, but this is something that had been seen before in the context of quantum extremal surfaces. In De Sitter Poincare, what we did was, for example, to consider bulk secret and the zero matter entropy in De Sitter at the future boundary, look at quantum extremal surfaces, and you're sort of forced to look at time-like separations. And for the DS2 case, it's this essentially becomes what these people have recovered, but more generally, you get this sort of structure. So this expression had been seen before, but I'm just sort of abstracting away and going to this context, and this is what you get. Okay. So this is DS3. Everything here is just direct, so to speak, just directly in De Sitter. But you could ask if one can get all these things by some analytic continuation, and you can, of course. So this is a standard analytic continuation for that goes between ADS and DS. So L is the cosmological constant, and this is ADS here. And under this analytic continuation, where capital L goes to minus I times small l, you get De Sitter. As far as the analytic continuation goes, you get it's just L squared that appears everywhere, so it doesn't really matter. But in the areas, there are extra things that happen, and so they actually pick out the sign of the imaginary part. For the now, if you want to ask for the analytic continuation how to track these ADS RT surfaces, the ADS RT surface for the IR for the full space goes from here, R goes to infinity here, goes all the way in and then comes back and so on. So I'm looking at a constant time slice to do this, for example. So the constant time slice is here in ADS. This now, under the analytic continuation, you can see that this thing still maps to something non-trivial on the De Sitter side. This expression flips sign as you go across, and this is the difference between the hemisphere and the Lorentzian part, and you can actually calculate what's going on. I'll show you the expressions very quickly, but very soon. But the ADS RT surface goes from the spatial boundary all the way in and back. In the De Sitter case, if you track this, you can see that R goes to infinity is actually the future boundary here. So it goes from here that way and then back. Okay, and that sort of the turnaround is in the hemisphere. Okay, if you calculate the areas for this maximal, so this is the top view, so to speak, of this. The red one is the IR, the maximal subregion. The blue ones are the are generic subregion. And if you look at, I'm just focusing on the IR subregions here. If you focus on the IR subregions and analytically continue this way, you can see that the areas in ADS continue like this, and you have to really break up this area integral into this hemisphere part and the Lorentzian part. this part ends up becoming half de Sitter entropy, and this part is time-like stuff. And there's subleading pieces here which could happen, which are there for higher dimensional de Sitter and so on. So for DS4 and DS3, you get these explicit things, and this is also what we got. But as you can see, if you change the sign of this to answer what you were asking, Ronak, if you change the sign of this, the analytic contribution doesn't change, but this thing will change the sign of the imaginary part, but this one will remain, and so on. So there is, but once you fix that, then you can ask about other things that happen relative to this, and then there is still some correlation between that, which is interesting. Once we have the analytic contribution, we can ask if there's a version of the Lipowitz-Maldacena story over here, and there is a heuristic version that I can come up with. I think there's more to be done here and more to be understood here, but let me just run you through this heuristic thing. So the Hartle-Hawking wave function universe, for our purposes, is an amplitude or a transition matrix for creating a universe with final boundary conditions from nothing. In other words, satisfying the Hartle-Hawking no boundary condition. Semi-classically, so this is the picture that we have in mind. This is Hartle-Hawking. Semi-classically, this wave function is just given by the action, it's controlled by the action, but the action has this top Lorentzian part where the action is purely real, so this thing is just a pure phase, and then there's this piece, which is the hemisphere part, which is the Euclidean gravity action, which is half de Sitter entropy, and this is well known from long back. The no boundary point here, NBP, is this point, this bottom, and in the conventions I've been using, this is pi over 2 in terms of the time coordinate that I'm talking about. Lefkowitz-Maldacena is a bulk, it is constructing a bulk ADS replica dual to a boundary replica entanglement entropy argument. So we start with the ADS CFT dictionary, ZCFT, Z bulk. So boundary entanglement entropy then becomes bulk entanglement entropy if you set up this correctly. Okay. So in a little more detail, if you look at the bulk replica space, we construct n copies with the n copies glued correctly across the interval and so on. Then we quotient that and construct the replica quotient space, which is where we quotient by the replica symmetry. There could be conical singularities which are smoothed by a codimension 2 cosmic brane source. Okay, the smooth action then is this. So locally, away from these conical singularities, everything is is just like a single copy, and so we get this sort of smooth action. But this is the brane action. Now, if you calculate the entropy using the replica formulation, you get the standard RT expressions, and the cosmic brane wraps all the transverse directions and so on. Okay. In DSCFT, the dictionary is ZCFT is psi ds. So the boundary replica via ZCFT looks like the bulk replica on psi ds, where this has to be really interpreted carefully. Okay, so I'm really doing a boundary replica, and I'm sort of just using this dictionary just for the purpose of this calculation, so to speak. I'm not really doing a really bulk calculation, so to speak. But if you do this and go through the motions, then what you end up with is that there's a bulk replica on a single copy of the wave function, which is a single ket Norder density matrix. And so this is not a Hermitian object. What you get is a pseudo entropy, which is the entropy of this transition matrix, interpreting this as an amplitude transition matrix for this event. Okay. And wow. All right.
Thing here, when you say you're not doing a bulk replica, then what exactly is this a calculation of? It
is simulating a bulk replica. I think what I have in mind is more, but maybe we should talk a little later if that's okay, because I still have a little bit to go, and then I'll get to that. If you go through the analytic continuation, then you can see that this thing localizes to the pseudo entropy of this IR surface. But the cosmic brane here is not space-like. It's a part Euclidean, part time-like, no boundary de Sitter extremal surface. And in this replica formulation, the entropy is really the area of the cosmic brane created from nothing. And the amplitude for this process would be divergent if the Lorentzian part, which goes all the way to I+, were real. Okay? Here, the time-like part is a pure phase, which cancels the probability, which is consistent with the fact that the finite part, which is the boundary real part, comes from the hemisphere, which is set by de Sitter entropy, and that's the most that you can have in de Sitter. Now, in the last little bit, I'm going to just flash through a little bit if I can take up like 2-3 minutes more, if that's okay. So in this last part, I'm going to talk about all of this stuff in just quantum mechanics. We've seen that de Sitter suggests these things where we start at these structures where where there's extra data required on the boundary conditions in the far past. So these are like scattering amplitudes in some ways, final states from initial states and so on, or equivalently time evolution. Okay. So one might ask, what do you get if you look at entanglement-like structures from the time evolution operator after a partial trace for the environment? So here what I'm trying to do is just blithely look at the time evolution operator in simple quantum systems as a density as a generalized density operator and asking for the mechanics of entanglement-like structures. If you do this, these resemble the usual finite temperature entanglement, but with imaginary temperature. And the objects that you get are closely related to pseudo-entropy, which is the entropy of the reduced transition matrix. In particular, if one starts with the time evolution operator and goes through this, you get certain structures. But this is the whole time evolution operator. It contains everything. If you look at components of the time evolution operator to simplify, to focus on certain components, what you get, you can include projections onto certain initial states. This then, this object is just the future state that you get from time evolving the past state, and that then is precisely the pseudo entropy from the reduced transition matrix for some initial state and its time evolved final state. Okay, so one can go through this in simple quantum systems like two-state systems, and what you get generically are complex objects, but in certain cases you get interesting real-valued expressions which don't look like entanglement entropy in any sense. In particular, this object, for example, is not bounded. It diverges at specific values and so on. For a general, but it's real valued if you again up to choosing the branch of the logarithm and issues related to that. A general 2-qubit Hamiltonian has this general structure where you get two phases coming from the time evolution. And if you project onto thermofield double type initial states, what you get are these structures where C1 and C2 are the components of the two states and of the two components of the state over here. I think, so this was all with one copy. You can ask what happens if you look at two copies, and for two copies, along the lines of those things that we saw for Go spins, you can see that in fact you recover certain positivity structures in some ways. Okay, but this is still sort of evolving. I think so I think in light of time I'll stop and leave you with these conclusions. Thank you.
So if we look at D+1 dimensional ADS, we can take, let's say, a totally geodesic subsurface, which will be a lower dimensional ADS. Yeah. What do you think is the meaning of that? Because the reason why I'm asking this question is that if I take inspiration from what you told us today, and I would think locally a piece of area which is partly time-like shouldn't care about the boundary conditions, like locally in the bulk. I should be able to extend it. What if I extend it, and I discover that I'm in ADS and not a DS? Then those surfaces should also have a meaning in ADS CFT.
So everything I'm saying here is specific to DS, and I would be wary about playing these same games in ADS because we know some nice answers there, and we have physical reason to understand those things in certain ways. So so I think so we can look at the detail thing that you're saying, but but I would be a little wary about doing this whole thing in ADS just by extension.
Question, like if we worry about doing it in ADS, then why should we be confident about doing it in DS?
So I think, if you ask for so this is what I said right at the beginning, if you ask for what this means and so on, I think there are questions. You get these structures called pseudo-entropy, but apart from calling it a name, what does this object really mean? Where's this going? I think this is still evolving. In DCTA, you're sort of forced to go to this just because there's just nothing that does anything else from the point of view of the future boundary. So that's what, so you're sort of driven to this structure. I think that's the best that can be done and so on. There are many things that sort of fit this pattern, but if you ask for a bigger thing, I think it's fair to say that we have to see.
Narayan, it seems to me that there's a sort of more general question beyond DCTA, which is Suppose you have a Euclidean field theory and you're trying to associate some notion of entanglement with it. How could you do it? So the obvious answer is, if you can continue the Euclidean theory to a Lorentzian theory, ask the question there and then somehow try to continue back. But that cannot be applied because we know that the duals to de Sitter break reflection positivity, therefore they cannot be continued in general to Lorentzian space. Okay, but
these are Bose-like theories.
No, not necessarily. So if you look at the obstruction to reflection positivity being true, then it could also be that the Hamiltonian you would arrive at in the Lorentzian theory is not Hermitian anymore. So there are two things that could go wrong. One is that you don't have a positive norm in the Lorentzian space, but the other is that the Hamiltonian you come to is not Hermitian. And that's what I was asking, was that maybe one could study just confirm that the Euclidean theories which break reflection positivity, but where the breaking is due to a non-Hermitian Hamiltonian. Maybe it's not such a crazy theory then. At least try to answer this question.
Yeah, I have nothing specific to say about this right now, but I think
just a comment.
Okay, let's thank Narayan again.